Okay, so in this video we're going to talk about sigma notation and Riemann sums. Riemann sums. Okay, so let me start by defining sigma notation. Okay, so sigma notation is a way to compactly write a sum. Okay, so if we have a sum like a1 plus a2 all the way up to an, we can write this as sigma I equals 1 to n of ai. All right, so let me talk about what each part of this expression means. So this 1 is the start value for I, and this n is the final value for I. And then this sigma, this Greek letter sigma, this means sum, all the terms. Okay, and then this AI is the general formula for the terms. Okay, so what this means is you're going to have a formula, AI, and you're going to put 1 in for I. Then you're going to put the next integer, 2, in for I. And you're going to continue putting in integers until you get to n. Then when you have all those expressions, expression with 1, expression with 2, expression with all the integers up to n, you're going to sum all those terms. Let's look at an example. All right, so let's find each sum that's written in sigma notation. So the first sum is going to be I equals 1 to 3 of I squared. And the second one is going to be the sum from I equals 0 to 4 of 2i plus 3. Okay, so let's work out what each of these means. So what this means, the sigma notation means, is we're going to put 1 into this formula, so 1 squared. We're going to put 2 into this formula, 2 squared. And then we're going to put 3 into this formula. And we're going to stop at 3 because 3 is our final value for I. And then we're going to add all these terms. Okay, so we get 1 plus 4 plus 9, which is 14. All right, I want you to stop the video and try to do part B, and then start it up again and check your work. All right, so we're back. So in the second part, we're going to put 0 in first. We're going to put 2 times 0 plus 3. Then we're going to put 1 in, 2 times 1 plus 3. Then we're going to put 2 in, 2 times 2 plus 3. We're going to put 3 in, 2 times 3 plus 3. And we're going to put 4 in, 2 times 4 plus 3. And we're going to stop at 4 because that's our upper limit, our final value for I. And then the sigma says we're going to add all these. Okay, so we'll have 3 as our first, 5 as our next, 7 is our next, 9 is our next value, and then 11. All right, if we add these up, these last two terms are going to be 20, and these first 3 terms are going to be 15. So together we'll get 35. Okay, so let's do another example, and in this example we're going to reverse this process. So in this example, I'm going to give you a sum, and I'm going to have you write it in sigma notation. Write each sum in sigma notation. So the first sum will be 1 plus 2 plus 3 all the way up to 100. And the next sum will be 1 plus 4 plus 9 all the way up to 81. And then f of 1.1 plus f of 1.2 all the way up to f of 5. Let me add one more term here. See the pattern more clearly. F of 1.3, and then all the way up to f of 5. Okay, so the first sum here, we just have to figure out the pattern. So it goes 1, 2, 3. So it's going up by 1. So we're going to start at 1, and we're going to end at 100, and we're going to just have each term be the index, the I. Okay, So it's going to be 1 plus 2 plus 3 all the way up to 100. All right, for this next example, we need to figure out the pattern between consecutive terms. And if we look closely, we'll see that the pattern is this. The first term is 1 squared, the next term is 2 squared, 3 squared, and then it goes all the way up to 9 squared. Okay, so now when we've identified that pattern, we know the formula. The formula in the inside of this sum here is going to be I squared. We're going to start at 1. We're going to put 1 into this formula, and then 2, and then 3, onwards, all the way up to 9. We'll end at 9. Okay, so for this last example, I have to rewrite this sum. I'm going to write it like this. I'm going to write it as 1 plus 0.1 plus 1 plus 0.2, and then 1 plus 0.3, all the way up to 1 plus 4. And I can see where the index is coming in here. I have 1, or 0.1, 0.2, 0.3. So let me rewrite this again as 1 plus 0.1 times 1, 1 plus 0.1 times 2, and 1 plus 0.1 times 3. And then the last term is going to be 1 plus 0.1 times 40. 4 is 0.1 times 40. All right, so now I can see how sigma notation is going to come in here. We have an index which is going 1, 2, 3 up to 40. So we're going to write this as I goes from 1 to 40, and then we just figure out what the formula is for all these terms. It's going to be f of 1 plus 0.1 times that I. All right, so sigma notation is a nice way of writing a sum and also capturing the pattern of consecutive terms. Okay, so in a previous video we talked about the Riemann sum. This will be my third example. So recall the Riemann sum for f of x from x equals a to x equals b was given by this formula. It was f of a plus b minus a over n times 1 times b minus a over n plus f of a plus b minus a over n times 2 b minus a over n plus, and then this continued on till we have f of a plus b minus a over n times b minus a over n. Okay, this is the area approximation using the right endpoints. Let me write that down. Using right endpoints. All right, so now we can rewrite this using sigma notation. Okay, we just have to figure out the pattern, and it's pretty clear what the pattern here is. We have this f of a plus b minus a over n times something each time, and then we have this b minus a over n each time. And the only thing that's changing is our index. We have a 1 here, a 2 here, and then this continues on up to an n. So if I write this in sigma notation, I'll say I equals 1 to n, and then the generic term, the general formula, f of a plus b minus a over n times I, all times b minus a over n. So this is a general formula for a Riemann sum. Okay, let's look at one more example. We're going to use this general formula to write the area approximation for a new function. So consider f of x equals x cubed over x equals 1 to x equals 5. And write the Riemann sum in sigma notation. Okay, so what we need to do is we need to use this formula that we figured out in the last example. Okay, so we have our a and our b. That's 1 and 5. So a is 1, b is 5. So b minus a is going to be 4. And we are ready to start putting stuff in this formula. So we'll have the sum from 1 to n f of 1 plus 4 over n times I, all times 4 over n. All right, we're not quite done because we have the formula for f. So we can write x cubed at the place of this f. So we'll take this 1 plus 4 over n times I, and we'll cube it. And then we'll be done. So you can think of this generic term, this general formula, as representing the area of our ith rectangle. Let me draw a picture here. So we have 1 to 5. We have this cubic. And we have some rectangle. Let's say this is our rectangle here. This is the ith rectangle used in our sum to find the approximate area. Okay, so what's the location of this point here? Well, this point is 1 plus 4 over n times I. You start at 1 and you go over I subintervals till you get to this point right here. And then you take that point and you put it in the formula. You put it in the formula, so you get a height. Okay, that's what this is. This is the height. This is the height. This is the input, 1 plus 4 over n times I, in the function. So this height is f of 1 plus 4 over n times I. And then we're taking that height and we're multiplying by the base width, which is 4 over n. This is the base width. And when we multiply those two quantities, we get the area. So this is a general formula for the area of the ith rectangle. And then the sigma I equals 1 to n is adding up the areas of all those rectangles, not just the ith rectangle, but every rectangle starting at the first right endpoint all the way to the last right endpoint. All right, I hope you found this video useful.